All right, we are going to look at simple harmonic motion graphing today, and there's a lot of information you can pull from these graphs. So the two graphs we're going to look at a mass spring simple harmonic motion of a position versus time graph, and we're going to pull out some different information like amplitude, frequency, period, angular frequency, maximum speed, phase shift. We're also going to look at an acceleration versus time graph and pull out some information like mass, amplitude, maximum velocity, and phase shift. And I'm going to show you both of these, and we're going to kind of work through how do we get the information from that graph and translate it into all these other different variables. So the first and easiest thing typically to pull from these graphs is the period, the time it takes to make one motion. So, for instance, this one starts at 4 centimeters and then 16 seconds later it ends at 4 centimeters. They basically gave me the period as being 16 centimeters. Sometimes you'll have to maybe look, okay, it crosses the line here, crosses the line here, what's those two times? And then double that because that's only half the period. Okay, so this case, it gave it to me. So I know my period was just 16 seconds. All right. So then I want to find maybe the frequency. So I need a relationship, and that frequency is 1 over the period. So I get 1/16 of a hertz, which in decimal form is 0.0625 hertz. So if you want to leave it as a fraction or as a decimal, either one is acceptable. We're now going to look for angular frequency. Now, angular frequency is a little bit different than regular frequency. Angular frequency, that is that image you have of a wheel spinning in this direction, but it looks like my finger is just going up and down and oscillating in that motion. Okay? So angular frequency is related this way in that omega is equal to 2 pi divided by the period. So there is this 2 pi here where we didn't have it before in frequency. And that's because this is measured in cycles per second, where this is measured in radians per second. And so if we plug in 2 pi divided by 16, we get 0.39 radians per second for our angular frequency. Angular frequency is a powerful one. It allows us to move into a lot of other places when we're talking about trying to find other variables. So the next thing we want to find is amplitude. Amplitude, you can look at the graph and find amplitude. It's really nice if a graph is centered on the 0 line. So for instance, this one you'll notice goes from -10 to +10. That's great. That means that it only moves +10 away this way or -10 away this way, and that's my amplitude, 10 centimeters. Centimeters, we do have to change that to meters, so my amplitude does come out to be 0.1 meters. All right. If it's not centered, what you do is you take the difference between the two, the top and the bottom, and then divide that difference by 2, because you really only want to know how far from equilibrium to the maximum displacement is it. That will give you the amplitude. Okay. Next, we're going to look at Vmax and Fie. All right, so for that, we're going to have to go in and we're going to have to look at some of our equations. So if you think about simple harmonic motion, we had those 3 basic motion equations, the position, the velocity, and the acceleration. And our velocity function we had was negative omega a sine omega t plus phi. And when I want to find the maximum velocity occurs whenever this sine function, sine of omega t plus phi, is 1. So I get my Vmax value, and I drop the negative sign because it's going to be going one way at one maximum, another way at the other maximum. So the direction I'm not too worried about. I just want to find more of the max speed. And so it is just omega times a, and since I had my omega already, I had that 0.39 times my amplitude of 0.1. That told me my Vmax was going to be 0.039 meters per second. Was how fast that was going to be. All right. So we get 0.039 meters per second. Now, how do you find phi? All right. In order to find phi, you basically pick a point. Now, we have a position versus time graph, so I'm going to go ahead and use my position equation. So I have x is equal to a cosine omega t plus phi. And I'm going to pick a point that I know and plug it in. Ideally, I have a point where time is equal to 0. That makes my problem just a little bit easier to solve. If you don't have a time equals 0, you can pick any other known point. So for instance, we could have picked this 16 seconds and 4 centimeters point. But here we go. We're going to go ahead and plug those values in. So I know that at 0 time, it should be at 0.04 seconds with an amplitude of 0.1. Cosine omega t is 0 plus phi. Go ahead and solve this. So when I solve that, I got phi is equal to 1.16 radians. And when you do solve this, make sure you're in radian mode to get the correct answer there. Because we are using radians per second times seconds plus radians, and then I'm going to use my radian mode on that cosine function. All right, my next graph looks like this. This is an acceleration graph. I did give us a little bit more information on this simple harmonic motion in that we have a spring constant of 2,500 newtons per meter, and we're going to try and find the mass, the amplitude, and the Vmax. Now notice, when I say amplitude, I'm talking about the displacement amplitude, not the maximum and minimum amplitude of my acceleration function. So, how do we do this? Well, first thing we need to find is we need to find period, just the same as we did before. So in order to find period, we're going to take the final minus the initial, and so I see that these times are separated by 0.2 seconds. So I can work out that we'll erase this here, that my period is 0.2 seconds. All right, from 0.2 seconds, I can get down to my omega. My omega value is going to come out to 31.4 radians per second. And again, I get omega using that same 2 pi divided by the period. Okay. So now that I have omega, now I'm able to do some more stuff. All right. So my next step is I want to find the mass. Now I do know this is simple harmonic motion for a mass spring system. So I know that omega is equal to the square root of k over m. So if I go ahead and solve this, I find that m is equal to k divided by omega squared, and I end up with a mass of 2.53 kilograms. All right, so I use the condition for a mass spring system along with the spring constant I did find to go ahead and figure out what kind of mass do I have on that spring that's oscillating. So I found the mass to be 2.53, and this is in kilograms. Next, I need to go ahead and find the amplitude. Okay, so thinking about what we did over here with the maximum velocity. So if I can find a maximum acceleration, so I think about my acceleration function is negative omega squared a cosine omega t plus phi. And if I think about when is this a maximum, the cosine function is 1. And I know what my omega value is, it's 31.4. I can figure out what my maximum acceleration is for my graph. It's negative 12 and positive 12. So I can plug that in, and so I get 12 is equal to my omega, which was 31.4, squared times a, and I find out that my amplitude comes out to be 0.012 meters. Now the amplitude, remember, is the thing that stores the energy. Okay? So what is the spring constant? What is the amplitude? That's what adjusts the energy. All right. Next, they want me to find Vmax. Now that I know the amplitude and I know the omega, we can use our same equation from before that Vmax is this. Go ahead, plug in our omega over here of 31.4 and our amplitude of 0.1012. You get a maximum velocity of 0.38 meters per second. And our last step is we need to go ahead and find the phase shift. So we're going to go ahead and we're going to pick a point that we know. Now you'll notice that this one does not cross the t equals 0 line. So we actually have to pick a point where we just know the value. So for instance, I know the acceleration is 0 at 0.1 seconds. So I'm going to go ahead and I'm going to use that acceleration function. So I got 0 is equal to negative of omega, which I had from before, my 31.4, squared times a. This value I do know is just 12, by the way. I could just make a multiple substitution there. I should have. Times the cosine of omega times 0.1 plus phi. Again, just plug in my amplitude of 0.12. My omega, I was going to run out of room, so I didn't write it out, is 31.4. Go ahead and solve that. Make sure you're in radian mode. Solve it for phi, and you get phi is equal to 0.318 radians. And you'll note that this does cancel out when you're solving. So it's just going to be moving this stuff over to the other side with the inverse cosine function and going on. All right. That's it.